Hello, everyone. This week, measures of central tendency, looking at the mean, the mode, the median. So let's go. See what we can do. Chapter 12. So in the same way that we might be able to describe you, your height, eye color, hair color, age, we do the same with statistics. It enables us to just with a few key figures, get some sort of measure of the typical sort of data set, if you like. It says, it's called measure of central tendency, but as we mention a few of these terms, you'll see that sometimes one or the other will become more important. And so we'll walk through that as we come to it. For example, the mode, the most frequently occurring piece of data, if you like. Easy way to remember it, mode sounds like most. So that will help you, hopefully. Let's have a look at this data set here. Or sometimes you could just have one mode, but sometimes you could have a bimodal distribution, it has two modes. There were at least two items of data that occurred, most frequently. So let's have a look at this data set here as we look through it. Yes, there is a mode. It looks like it's 5. 5 occurs more frequently than any other piece of data. And I've said here, if you were trying to work out, how many shoes you need to produce, but potentially you'd be interested in, well, what is the most frequently purchased size rather than the average size or the mode has its place. Here we go. If we had a frequency distribution in this one here, for example, we look down the frequencies, we can see the highest frequency is 6. Of course, the mode isn't 6. The mode is the score that occurs most frequently. So it's the score of 2. 2 houses is the mode in this data set because it occurred most frequently. If we have a grouped frequency distribution, if the question just said in which interval is the mode, that's very easy. We can just pick the interval or the group where the mode occurs. But if we have to try and estimate it, we'll be given this formula. You won't have to remember it, but there's a fair bit of work involved in solving it. We might just have a quick look at it now. So we look at our grouped frequency distribution here, and we just immediately can identify that, okay, look, the largest frequency occurs here in this group. So if the question just said, where did the mode occur, in which group, you'd say, yeah, 7 to 13. But if it said, now I want you to estimate the mode, we have to apply this formula. So firstly, we identify where the interval is, and we know it's there. And then we've got to gather the data around that group. So L in our says the real lower limit of the modal class. Well, there's our modal class, but it's interesting. If something was 6.5, we'd round it up and it'd fit in this grouping here. 6.49 perhaps. Anything lower than 6.5 would be rounded, fit in with this group here. So therefore, the real lower half of this interval here, we've got to drop it down to 6.5, halfway between 6 and 7. So we've got 6.5. Then we've got to look for, and we'll see in a moment that what it tries to do is estimate, well, we don't know where the mode is. Was it 7? Was it 8? Was it 9? And by looking at the frequency in the class interval before and the class interval afterwards and doing an average and the difference between the current frequency, we can sort of estimate where we think the mode might be. Is it 10? Is it close to 11? Or is it closer down at this end? So let's have a look at how the calculation goes. D1 says I need to find the frequency of the modal class, which is there. It's pretty easy. Minus the frequency of the previous class. So 203,200 minus 189,200 gives me 14,000. So that's what will go up on the top of our formula. So filling in the formula, the estimate for the mode, the lower class interval 6.5 plus 14,000. Now then we're going to divide it by 14,000 again, plus what's D2? The frequency of the modal class minus the frequency of the next class above the modal class. So 203 minus 141, 800. Find that piece of data, plug that in down the bottom, and then multiply by the class width. So 13.5 minus 6.5. The top end of this bracket, 13.5, and the lower end, 6.5. So we've got a class interval of 7, so we're multiplying by 7. Now, interestingly enough, of course, we need to put that in brackets, make sure we do all of, do the addition before we follow the order of multiplication. I'd be tempted to use memory, for example. Once you've put that in memory, you could go 14,000 divide by whatever you had in memory, multiplied by 7, and then put that back in memory, and then go 6.5 plus recall memory, and practice that. Have a go, even pause the video right now and see if you have a go at plugging that data in and seeing if you get 7.8. If you follow the rules of mathematics, you should get 7.8. We will do it and practice it in class as well, but why not give it a go now? Make sure you can enter the data correctly and get the right result. The median. The middle observation set, excuse me, would have 50% of the data above it, 50% below. Another way to remember that, possibly, if you're a driver, is to know that the median strip is the middle of the road, that strip down the middle of the road. So if that helps you remember the median. Let's go and have a look at what we're going to do if it's an even numbered set of data. So if it's odd, it's pretty easy. We get the number of pieces of data in our data set, add 1 and divide by 2, and it'll be the one right in the middle will have the same amount below it as the same amount above it. But if it's even, we've got to find the observation of the n on second score, if you like, over n divided by 2 plus 1. Sorted observation. Let's have a play with it and see what we can do. This data set here, let's count them up. The first thing we need to do when you're trying to find the median is order it from lowest to highest. So we reshuffle the figures and find the lowest figure, put that first, then go looking for the next highest figure, cross it off. If you have to do it manually, find the next one and keep working up. So you've arranged it from lowest to highest. Let's count how many we've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It says 12. Let's check. I can only see 11. They are saying 12. Did we miss something? So a bit of a typo error in there. If there was 12, looks like they've forgotten to put something down here. Let's count them here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 12 pieces of data at the top. Something is missing down the bottom here. Let's imagine they got it right, and there's the 12th piece of data down the bottom. You could stop the video and work out which one they missed if you like. But the deal would be it's even. So we'd have to go, well, 12 on 2 is the 6th, and 12 on 2 is 6 plus 1, and the 7th, it's the average of the 6th and 7th score. So it looks like they missed something in the middle because if we did this right, if we really had 12 there and we find the average of that, we would find we'd have 6 scores below it and 6 scores above. So they're missing something up this end. So the average of those two, 260.5. Just spotted that now. But anyway, there it is. What if we added one more piece of data? And it's now we've got 13 pieces of data. 13 plus 1 is 14 on 2. The 7th piece of data should leave exactly 6 below it and 6 above. 1, 2, 3, 4, 5, 6. The 7th piece of data is the median. 1, 2, 3, 4, 5, 6. 6 above it. Median 263 because it was odd. There was one piece of data right in the middle. What are we going to do if it's in a frequency distribution? Easiest way would be to do a cumulative frequency. 10 plus 12 is 22 plus 16 is 38. Half of 38 is it's even. Half of 38 is 19. So we need to find the average of the 19th and the 20th observation. So we look down and we say, where did that occur? Oh, well, look, the cumulative frequency here is 22. So it must have occurred, the 19th and the 20th must be number 2. And you could reconstruct this piece of data. Essentially, we've got 1 occurring 10 times, then 2 occurring for the next 12 times. So 2 right in the middle would be fine. There would be just as many pieces of data above it. And of course, because it's 2, we didn't need to average it. We know the 19th was 2, the 20th was 2, the average of 2 is 2, so the median is 2. Again, it's quite laborious if we had to try and estimate where the median might be if we've got a grouped frequency distribution following a similar sort of formula, I guess, very similar to our quartile distributions. So again, we're going to follow this formula here. We've got all of the frequencies, we've added them up, and we know the median then, it is even. It is even. So when you divide that by 2, you get 1,561,950, and the 1,561,950 first. We added 1 to it, so same sort of deal there. And then we go looking in there and saying, well, where is 1561? So when we look down here, we can say, wow, 1561, if this is cumulative, must be in this batch here. So we know if the question just said, in which class interval did the median occur? You could say, oh, age bracket 25 to 34. Problem solved, nothing left to do. But if it said, now, I want you to estimate what the median would be, we'd have to apply this formula here. Again, same sort of principle, because it goes to 24 and 25, 24.5, if somebody who's 24 and a half, they'd go into this bracket. So the lowest observation is 24.5, n on 2, so that divide by 2, plugged into our formula, minus the cumulative frequency distribution, which is the cumulative, the cumulative frequency in the class immediately before the median class. So there it is, 719,500, the class immediately before. So we've put that in, over the frequency, what's F? The frequency of the median class. There's the frequency of the median class. Plug that in, and then multiply by the class interval. So here in our class interval, 34.5 minus 24.5 is 10. So we plug it all in. Again, if you wanted it, it'd be worthwhile just making sure you did this first, then subtracted that, put that in memory, divided by that, then multiplied by 10, put that in memory, and then get 24.5 plus 9.7, and hopefully you get 34.2. Again, it'd be worthwhile just pausing the video, crunching those numbers to make sure you got that figure. That would give you the confidence that your clerical accuracy is pretty good. Well, what about the mean? Just really all we've got to do is add, it's an average, add up all of the pieces of data and divide by the number of observations, number of pieces of data we have. If it's a sample, we've got this little X with a bar. If it's the population mean, if we don't have a sample, we've got all of the data, we'll be using this Greek letter mu. On the calculator, we would go second function alpha 0, 0 to clear all the memory out. We'd make sure we're in stat mode 1, 0 for single set of data, SD, you'll see on the screen. Mode 1, and you get a choice of 0 for single set, 1 for line, and 2 for quadratic. So we'll go mode 1, 0, and we're good to roll. And all we do is if the first piece of data was 45, press 45 and then press enter. Second piece of data was say 23, 23, press enter. Keep going, entering the data, and when you're finished, entered all the data, you can watch the screen. It'll tell you, you know, data set 1, data set 2. So if you forget where you're up to, you can count from the screen where you're up to. And finally, when you're ready, just recall. 4 will give you the mean, the set of data. In a couple of weeks' time, recall SX, standard deviation for the sample. Recall 6 will give you the sigma x, the standard deviation of the population. But right now, recall 4 will give us the mean of the set of data. So we've got some data there. If we just wanted to do it manually, add up all the pieces of data, 318 divided by 10. So on average, 31.8 looks about right when you look at the data set there. 31 looks to be the average there. Sometimes 34, sometimes 28. 31 looks reasonable. Always a good idea to check your answer for reasonableness. Make sure it looks okay. If I got that answer there and I added it up and I got 52, I'd say, that can't be right. Average has to, there's my lowest 28, there's my highest 34. Anything outside of that, anything in the 40s or 50s or, you know, less than 28, the average was 25. No, it can't possibly be. The average has to lie within the data set. So check your work, just make sure you haven't left a figure off accidentally or something. What if we've got a frequency distribution, add up the sum of the frequency times the data set, divide by the sum of the frequency. Let's have a look. So here's our distribution, got the frequencies, multiplied out. 0 times 15 is 0. 1 times 12 is 12. 2 times 16 is 32. Add up all the frequency times the data. We've got 104. Add up the frequencies. We've got 60. And divide it, 104 divided by 60, I get 1.73. Go back to your data, check it for reasonableness, and looks about right. The average, 1.73, sitting about there. All the frequencies seem to be floating around there. If you got an answer of 4 or 5, you'd say that can't be right. There's not a lot of frequency floating around in this area. The frequencies seem to be weighted around here. So that's pulling my average down to about that figure. Looks reasonable. Again, for us with our data set, still one set of data, mode 1, 0, but to enter our X data, we hit the XY button, and for the frequency, we hit enter. So to give you an example, we'd go, okay, first piece of data is 0, so I press 0 and then press XY. And the frequency was 15, so press 15, press enter. Second set of data, 1, so I'd go 1, press XY. Frequency, 12, 12, press enter. And as you do each time, it'll tell you data set 1, frequency 1, data set 2, you know, you'll know where you're up to. So if you've got down to the 5th set of data, you'll know you've got it all. Same sort of deal. Recall 4 will give you the mean. Well, what if we've got grouped frequency distribution? Let's have a look at it. Grouping here. The deal is the mathematicians say, well, we've said this before. Where does that 271, was it closer to 45 or was it closer to 59? The mathematicians say, look, let's find the midpoint. That's an estimate of where we think it's reasonable to assume for our calculations that that's where it'll be. So take the lower end of the class interval and the top and divide by 2 to find the midpoint. Find all of your midpoints. Once you've got your midpoints, multiply your frequency by your midpoint now. That's going to become your new X figure, if you like, your new XY piece of data if you're using the calculator. So if we were entering it on the calculator, it'd be 52 XY, 271.2, enter. 62 XY, 642, enter. Remember though, you need to, when you get onto a new question, second function alpha 0, 0 to clear out your memory. But essentially, we're doing it longhand. We multiply the midpoints by the frequency, we add it all up, and then we divide the frequency by the midpoints by the sum of the frequency, and we get an answer of 64.97. Does that look right? And when you look at the data set, it's sort of floating around most of the frequencies here. So that looks about right, that our mean, where the average would be sitting in that zone there. So looks good. What about a weighted mean? Here in this particular example, our assignment, we've got assignments worth 15%, projects worth 25. And what if somebody got 83 in their assignment, well, we'd give it a weighting of 15, and they got 72 in their project. So 72 times 25, and they got 41 in their midterm paper. So we just keep using the weights and divide by the sum of the weights, divide by 100, and we get an average, a weighted average of 57.45. We'll do a few more of those in class. What about quartiles? Very similar sort of calculation to the median. So the quartile 2, Q2, is the same as the median. It's right in the middle. Half the scores will be above, half the scores will be below. The Q1, quartile 1, will be the bottom quarter. 3/4 of the results will be above that point and 1/4 below it. And the same Q3, or quartile 3, would be the top 3/4. The interesting thing, when you find Q3 and Q1, you can subtract. The interquartile range is the difference between quartile 3 and quartile 1, the middle 50% of data set. Yes, 25% will be above this and 25% will be below this, but this will be the middle 50. Sometimes statisticians find that helpful because there could be some outlying, what do we call it? Unusual pieces of data, like a huge, imagine up here we had 500, and we'll call it an outlier. It's just an unexpected piece of figure, which is distorting the data set. It's just one unusual piece of data. So that middle 50% is helpful for us to solve. But anyway, let's look at the lower quartile. How are we going to do it? We've arranged the data, 16 pieces of data from lowest to highest. And because it's even, the bottom quarter, we've really got to average the 4th and the 5th score. 1, 2, 3, there's the 4th and there's the 5th. They both happen to be 9. So that piece right there, the value of 9, has a quarter below and 3/4 of the data above it. What about when we find the 8th and 9th score? Because it's just like the median we did before, the half of 16 is 8. So the 8th and 9th. So there's 1, 2, 3, 4, 5, 6, 7, 8. There's the 8th score. There's the 9th score. We average the two. We get 9.5. And 9.5 has exactly half the values below it and half the values above it. So there's our median again. We'll do something similar with the Q3. We'll practice that in class. And we'd use this formula, again, probably very similar to the median. We really do have to, I won't do the whole thing with you, but I'll just start it off anyway. We know that total frequency is 12,576. Divide by 4, it is even. So when we divide that by 4, we get 3,144, and the extra 1. So we're looking for those two, and where do they fit cumulatively? The 3 millionth score in their thousands. So it sits in this bracket here. So we've found the lower quartile class. We do something similar for the upper quartile. I won't bother with the full formula here, but just to point out, this time we didn't need to round it down because it's going 15 and under 18. So in other words, 17.98, will squeeze in here, and the lower quartile, the moment it's 18, it sits in this quartile. So we know that the lower bracket for this batch here for our lower quartile is 25. We didn't need to round it down to 24.5. No, 25 is good enough. That is the real lower limit of the quartile class. And then we plug all the data in. Again, if you wanted to practice your calculation and solving techniques, you might want to have a play with that. The geometric mean here is where we've got percentage changes. Whenever you get percentage changes, the difference between the population here and here, grab that difference, put it over what the population used to be, and we find that the change between that figure and that figure is 1.399%. Now, when you try and find an average for percentages, the best way to do it is not to just add them up and divide by the number of percentages, but we use the geometric mean for percentages, which means we multiply all of the percentages together and work out how many there are. 1, 2, 3, 4, 5. Because there's 5 of them, we'll take the 5th root of that. And so once you multiply it all out, find the 5th root, we get 1.588. Well, we'll test that in a minute to see if it's realistic. How would we do it on the calculator? Again, 1.568 times 1.399 times 1.738. Keep multiplying it all out. Hit equals. I would go store A, whack it in memory location A for a moment, and then we want to find the 5th root of it. So you've got to push the 5 first and then pull up the root key. So on the screen, 5, then second function bond will pull up the root key, the 5th root. You've just told it you want the 5th root of what. Once you hit bond, it's saying the 5th root of what, and you'll go recall A. Will bring back that 1.588 figure, and then you'll press equals and practice that if you like. Once you hit equals, you should get the answer of 1.588. So you might want to practice that. If you're using a different calculator, just find out how its 5th root works. But I'm going to stay with the financial calculator for us. Let's test it. You use our knowledge from about week 2 or 3 to use the compound interest formula to see if it's reasonable. So the first thing you might want to do is that 1.568 is bringing forward the change from the previous year. So we're going to work backwards to work out what the previous year must have been. So 100 minus, it was a 1.568 increase, means that it was a 0.98. If we find 0.98 of the population there, we'll have what the population must have been at the start, the end of year 2009 or the start of year 2010. So the value was 21,681. So we'll make that our PV, our present value. And then we'll make our growth is, we've got 5 years worth of growth, and hopefully we'll get to that figure. So we'll go, that's my PV, n equals 5, and we'll use this average growth, 1.588, and sure enough, it comes out at 23,458, which is pretty close to the figure. And of course, the difference is that 1 year it was slightly higher than that 1.568, so we've got a little bit more accumulation happening here. And when did that compounding factor occur? So we could be pretty confident that this geometric mean formula is working fairly reliably for us. And there would be a time when it would be helpful to just use that average to project into the future. Well, we're going to look just for a few more minutes at skewness. So here we've got a distribution. Whenever you get a distribution, we've got, so here's, the lower end, 0, for example. Imagine we're measuring heights of people. Now, heights of people would normally be distributed like this, a normal distribution, where we've got a few, shorter people down this end of the spectrum, and then the average right in the middle, mean right in the middle, and the most frequently occurring height right in the middle, and the median, of course, right in the middle. And then as we go up, the taller people, as we're getting taller and taller and taller, and finally just a few really, really tall people up this end. So there we go. It is symmetric distribution. Here we've got a distribution that is negatively skewed. Easiest way to remember it is look at the tail. The tail is to the left. Left has got an E in it, so is the word negative. So if the tail's coming to the left, think negative. What's it look like? Median will always be in the middle. Mode will always be the highest point of the graph, the most frequently occurring score. And it's these low scores to the left that are dragging the mean to the left of the midpoint, the median, and so the mean will be to the left. Have a look at it. If it's positively skewed, another way to help you remember is to look at the tail and think of the word, I'm positive I'm right, and tails to the right, I'm positive I'm right, it must be positively skewed. I'm just a little memory jogger there that might help you if you've got a multiple choice question that said, hey, is this negatively skewed or a positively skewed? You'll look at the tail and say, I'm positive I'm right, it's positively skewed. Anyway, median, right in the middle, mode, highest score, highest point of the graph, and the mean, these high scores are dragging the mean to the right of the median point. This little formula, the coefficient of skewness, says, give me 3 times the mean minus the median over the standard deviation. So let's have a play with just one of them. If you get an SQ figure that is less than 0, it's negatively skewed to the left again. If it's skewed, if the greater than symbol comes out, if the skewed figure is greater than 0, positively skewed to the right. Skew equals 0, no difference there. So we'll just look at 2. So here, mean 26, median 26, standard deviation 12.3, 3 times. There is no difference here between the mean and the median divided by the standard deviation. And we end out with 3 times 0 divided by 12.3, we get 0. So there's no skewness there. Let's just look at this bottom score here, where the mean is less than the median. So we get 23 minus 26 is minus 3. Minus 3 times 3 is minus 9. Divide by 12.3 and we get minus 0.73, negatively skewed. And of course, positively skewed this way when mean is 29 and median's 26. Well, next week, we're wrapping up this week, but next week we'll be looking at probability and just something to think about between now and then. And I thought this was interesting. What is the probability of you being you? How unique are you? In other words, what's the probability of finding another person whose DNA is identical to yours? And so we've got to look at the DNA rudder, and a ladder, I should say, and a base pair is 2 chemical bases bonded to one another, forming a rung on the ladder. And how many of them are there? Well, each human being, we're separated by 6.4 million base pairs. So the chance that 2 people are genetically identical is 1 over 2 to the power of 6.4 million, which is the same chance of getting heads 6.4 million times in a row with a toss of a fair coin. Think about that for a moment. So you are pretty unique. You could chase these sources up. Science in our world, certainty and controversy. Can 2 people in the world be identical? They look at it and there is our answer. And you might say, well, what about identical twins? I thought they shared the same DNA, and they do, but there are some genetic changes that are happening very early in the womb, even though they're sharing the same DNA. Interesting. It sort of just alters the structure somehow. One last thing to think about with mathematics and probability. In order for you to be born, you needed 2 parents, makes sense, 4 grandparents, 8 great-grandparents, 16 second grade, and it just keeps going down to 2048 9th great-grandparents. So for you to be born today from 12 previous generations, you needed a total of 4,094 ancestors over the last 400 years. Now, possibly there's a little bit of overlap and double counting in there, but perhaps not that much. And I thought it was just fascinating just to ponder for a moment, just to let your mind wander and think about that for a second, where you've come from. And maybe you don't have to go back too many generations before perhaps some of these people were speaking a different language even than you are speaking today. You know, would these guys understand you? if you were speaking with them. But what was their life like these last 400 years in the 1600s or 1700s, some of these ancestors, or the 1800s or the 1900s? And what would they think and feel if they time traveled to today to meet you and have a chat? How would they compare their life and lifestyle to yours? What would they think when they saw you flick on the flat screen TV or your mobile phone and show them around? I guess, you know, they'd be blown away. Imagine I would be if I'm coming forward from the 1600s. Would they want to swap places with you? And would you want to swap places with them? Something to think about. We'll be looking at delving into probability next week. Looking forward to catching up with you then. And hopefully by today, you know, from today's session, you've had a bit of a look at the mean, mode, and median, got a bit of an understanding of what the quartiles are doing. Lowest quartile 1, quartile 3, bottom quartile, top quartile, and you could go over that. We'll work through a few examples when we get together in class. Looking forward to catching up with you then.